Okay, well, good morning, good afternoon, good evening, depending on where you are. So the title of my talk is actually somewhat presumptuous because I haven't actually measured any radial velocities for the sun as a star in this talk. But what I'm going to say has implications for line-by-line radial velocities. And I want to begin by acknowledging my collaborators, Joe Lama at Lowell Observatory, and Guanwei Fu, who was my former student. He's now a postdoc at Johns Hopkins. And what I'm going to talk about in this talk is, first of all, why we care about the sun as a star. And I think it won't be too hard to convince this group that we should care about the sun as a star. And then I'll talk about two approaches to measuring precise radial velocities. And I want to add a little historical context because I think it's valuable to understand how we got to these two approaches. And then I want to mention briefly something about the taxonomy of false radial velocities. There are lots of effects that can cause false radial velocities on the sun, and many of them are well known. Some of them are maybe less well known. And then the main part of my talk is to talk about line shapes, specifically line bisectors, measured by the SOLIS project, and I'll explain what SOLIS is. And in particular, I want to investigate how to separate changes in the shape of the line from changes in the radial velocity shift of the line. And then at the end, I'll talk about what's next, i.e. what we're doing now this summer, and I'll summarize. And if you're interested in line bisectors, almost everything I'm talking about today is in a paper that appeared in the Astronomical Journal in January of this year that talks about line bisectors in the SOLIS data. So the sun is great, particularly if you're a graduate student doing a thesis. You have to have data, and it has to have a high signal to noise. If you work on the sun, the first advantage of the sun is it's bright. There are lots of photons, and we can resolve the disk of it. So if you're a graduate student, your PhD thesis, you're guaranteed to have good quality data. And because we can resolve the disk of the sun, we can learn about the nature of false radial velocities. And this image is a spectroheliogram of the sun in a line that's sensitive to the chromosphere. And the bright regions are magnetic regions, which are very prevalent on the sun, especially as the sun becomes active. And these magnetic regions cause false radial velocities in various ways. And the principal source of false radial velocities is ultimately solar magnetism. Now, there are two approaches to measuring the radial velocities of the sun as a star or of stars. And I want to talk a little bit about how those approaches developed in the history of astronomy. The first is a line-by-line method. You measure the radial velocity of each individual absorption line. And I'm talking about line-by-line spectroscopy today, but I certainly didn't invent it. It's been applied it's been applied to stellar spectroscopy for decades, and it's been applied to the sun at least for a number of years now. And the second is a cross-correlation method, which really dominates current methods for measuring radial velocities. And the historical context is in the 1970s and earlier, stellar radial velocities were very often measured on a line-by-line basis, but the detectors were glass photographic plates. I still have some of them in my office from spectra I took in those days. And the glass photographic plate was dimensionally sort of stable, at least compared to the precision that was achieved, limited by other factors. But they otherwise were bad detectors. They weren't very sensitive. They didn't have very high quantum sensitivity, and they were nonlinear. And this is an image of a spectrum on a glass photographic plate. And this is actually a good one. This is the sun made at Mount Wilson, and the stellar spectroscopist would measure when photons hit the photographic plate, they darken it. And the light regions, which are vertical lines here, are the absorption lines where not much light has hit the photographic plate. And astronomers would measure the positions of those lines. And back in the 1970s, my thesis advisor was doing stellar spectroscopy, and he was very happy to have a precision of 1 kilometer per second. It began to change. The first big change for me was in 1967, with this paper by Roger Griffin called a photoelectric radial velocity spectrometer, in which case he did a cross-correlation analysis. He dispersed the stellar spectrum and transmitted it through a template, a mechanical template, and then recollected all that light and focused it on a photomultiplier detector. So a photomultiplier was an electronic detector, but essentially only a single pixel, but it was much more sensitive than a photographic plate. And by then changing the relative position of the spectrum on the template, he could do a cross-correlation, essentially a cross-correlation analysis. And the advantage of this, well, it didn't improve the precision. The precision was still 1 kilometer per second, and it was limited by things like flexure in the spectrograph and other effects like that. But it was much more sensitive. So it was for me, it was the first cross-correlation radial velocity spectroscopy, and it was more sensitive. So it extended to fainter stars. Then in the 1970s, CCD detectors were developed. And those were the real big development that enabled really precise high signal to noise stellar spectra, plus the advent of stable spectrographs. And now we have laser combs, and line-by-line radial velocity precision is immensely improved. Cross correlations are still valuable and are still dominant here. But now you don't do a cross correlation mechanically by moving your template. By moving a mechanical template like Roger Griffin did, you calculate them analytically. So there are a number of sources that can cause false radial velocities. And I actually want to discuss this slide from the bottom up. So go down to the bottom. Steve Saar gave a colloquium on magnetic intensification. So if you have a spectral line at one that's affected by one spot on the solar disk by a magnetic field, the magnetic field can actually increase the strength of the line without necessarily increasing the asymmetry of the line. The line can be perfectly symmetric, and its velocity cannot be shifted, but its strength can increase. And the reason that happens is if there's a Zeeman splitting in the line, then for a saturated line, the line becomes stronger because the Zeeman splitting gives more frequency space available to absorb photons. The line strengthens. If the line strengthens in one region of a rotating star, then that overweights that region in the integrated velocity of the star, and will give you a signal in integrated light that's a radial velocity change. So line strength changes can change stellar radial velocities. Then going up a little further, there's line blending. Line blending needs a better press agent. It isn't very often discussed, but when the temperature in the photosphere of the star changes, and it changes due to magnetic regions, like the umbra of sunspots can be thousands of Kelvin cooler than the photosphere, that will cause the spectrum to change, and low excitation lines can blend with the usual photospheric spectrum, and those line blendings can cause a radial velocity effect. Then at the top, there is the magnetic inhibition of solar convection, granular convection on the sun. There are upwelling hot regions and intergranular lanes that are downwelling that are cooler. And because the hot regions are brighter, they dominate, and solar lines are on the whole net blue shifted, but the line is asymmetric. And the bisector, remember the bisector is you at a given flux level, you find the spot on each flank on the red side and the blue side of the line, and you average those two wavelengths, and that's the bisector. If the line were symmetric, then the bisector would be this vertical dashed line here, and that would be the centroid of the line. When the line is not symmetric, the bisector is curved, and then you have to decide what's the centroid of the line. If you're measuring changes in radial velocity, which is really all we care about, then if the bisector is constant, then you can just look at changes in the bisector, shifts in the bisector. Now, I want to talk a little bit about line blending. I'm going to mostly talk about line bisectors that are affected by the magnetic inhibition of solar convection. This top panel here is the principal part of my talk. But because line blending needs a better press agent, I want to give it a little discussion here. So the sunspots and also dark pores. At any time on the disk of the sun, especially when the sun is active, there are numerous small dark pores, which are like the umbra of sunspots in that they're very much cooler than the photosphere. They can be arc seconds, only a few arc seconds in diameter, and thus not very noticeable in synoptic images of the sun. But there can be, at any one time, there can be 100 of them on the disk of the sun. And this spectrum is the spectrum of the photosphere. This is Fourier transform spectroscopy. It's a spectrum of the quiet photosphere and the spectrum of a sunspot. And I just picked a region where line blending varies quite a bit between 3 lines. The nickel line on the left, you can see that now the sunspot in this spectrum it's a whole sunspot. The blue curve is the entire sunspot. In the integrated light of the sun, that sunspot is only a small fraction. So you take a small fraction of that blue spectrum and add it to the photospheric spectrum. But when you're talking about, you're trying to measure 9 centimeter per second radial velocity, even a small amount of contamination can be a big problem. The nickel line on the left that's a bad effect. The iron line in the middle is even worse, and the iron line on the right is really bad. So different lines can be affected by line blending to a different degree. This line at the longest wavelength here, I would expect that in the spectrum of the sun as a star, that line would be a real problem because it will be blended with cooler lines from dark pores and sunspot umbra when the sun is active. So lines are affected to different degrees, and so a line-by-line radial velocity analysis can really help to isolate the lines that are the best behaved and the lines that are the worst behaved. And then even if you're doing a cross-correlation radial velocity, you can apply a weighting factor that will low weight the lines that are not behaved as well and give more weight to the lines that are well behaved. So this subject of can you discriminate now between line shape changes and line shift changes? Well, I've thought about it for a long time, but I don't come to solutions very quickly often. So the real solution, one real solution was in 2021. Andrew Collier-Cameron, Eric Ford, and their collaborators, they showed that you can separate the Doppler shift from the effects of line shape changes in the cross-correlation function using an autocorrelation analysis. So the question that immediately arose to me is, well, can I do the same thing if I just have a single line profile? Can we do the same thing in a line-by-line analysis? And the way to investigate a line-by-line analysis, well, you can do it now. We can do it with spectra from NEID and EXPRES and KPF and other spectrometers, HARPS North, but there's also SOLIS. SOLIS is a project of the National Solar Observatory, and I always want to think that it starts with solar. It doesn't. It starts. SOLIS is synoptic, optical long-term investigation of the sun, and it's more than just spectroscopy of the sun as a star. It's imaging also. It's imaging and spectroscopy, but it includes spectra of the sun as a star using the Integrated Sunlight Spectrometer, the ISS. And the ISS is a double-passed spectrometer, has a resolving power of 300,000. Now, perhaps unfortunately, they don't take spectra of the entire, panchromatic all wavelengths of the sun. They select 10 segments of width, whose width and wavelength varies from about 1/2 to about 1.6 nanometers. And those segments are centered on key lines, for example, the H and K lines of calcium that are sensitive to the chromosphere, but also some other lines that are just sensitive, some other segments that are just sensitive to photospheric lines. And even there are even lines in those segments which are just incidental to the line that SOLIS was really targeting. And we use for our analysis 21 photospheric lines in 5 segments, and we measure line bisectors. In total, we measured 62,325 bisectors, and that might seem like a lot, but compared to the quantity of solar data that's being acquired now by spectrometers like HARPS-N and NEID, that's not very many. So one big advantage of SOLIS is that it covers all of solar cycle 24. It began in 2006, and it was temporarily decommissioned in 2017 because the facilities on Kitt Peak were closed down, and SOLIS is being relocated to Big Bear. So it will start up again. And I keep hoping it will be ready any day now, but it hasn't started up again. But nevertheless, it's covered all of cycle 24. And this plot, the black line where you read the y-axis on the left is the number of sunspots. And you can see there's the big burst of activity in cycle 24. The gray line above the black line is the mean magnetic field on the sun. And you read the axis on the left. And when the sun becomes active, the mean magnetic field increases by a factor of several. The value of 6 Gauss is what we've used to separate active and inactive phases of the sun. These horizontal lines are the temporal extent of the data. And SOLIS covered all of cycle 24, but then has been decommissioned temporarily and being moved. But HARPS-N started up in 2015. EXPRES has recently started. NEID has started monitoring the sun. We'll have lots of data for cycle 25. Also KPF. I made this figure before I realized that KPF was up and running. So there'll be lots of spectrometers. There's also Pepsi, which I didn't put on here. So here's an example of a segment from the SOLIS data. This one is centered on the neutral carbon line at 538 nanometers. That's a very interesting line because it's high excitation, and thus it's formed deep in the photosphere. So it may be sensitive to velocity trends that are deep in the atmosphere. Unfortunately, it's also a very weak line because it's high excitation, so it's not extremely, the lower state isn't extremely heavily populated. But here are some, in the lower panel here, I've just replotted the lines on a greater scale with the bisector measured. So now, there's no laser comb in SOLIS. There's no absolute wavelength calibration. So we can't measure the radial velocity directly, but what we can measure are line shapes. Instead of a direct wavelength calibration, they shift the spectra to a common frame. In other words, they shift them all to coincide together in wavelength. They actually use high-resolution Fourier transform spectra as their basis for comparison. They shift them so that the wavelengths agree with the FTS spectrum. And the FTS spectrum itself is not absolute wavelength calibrated, but in this case, in our analysis, we don't care so much about the absolute wavelengths. We're going to inject a signal, and then we're going to see if we can recover it in the presence of line shape changes. Another advantage we have is that it's both an advantage and a disadvantage. They've already determined where the continuum level is. They've rectified the continuum level. So that means that our analysis here to measure a bisector is very simple. All we have to do in our analysis is draw a line across the spectrum at a given flux level and find where that line crosses the red and blue flank of each absorption line. That involves some interpolation. And we're interested in the effect on really precise radial velocities when the bisector changes. So we have to measure the bisector very precisely. And we have to do that interpolation very precisely. So what we first do is we Fourier interpolate the spectra to a much denser wavelength grid. And then even that dense wavelength grid is you can't just pick the points out. You have to still interpolate between points. And we use a quadratic interpolation. We spent a lot of time testing our interpolation method. One way to test it that we used is you make an analytic line. We know what a Gaussian line looks like. There's a formula for a Gaussian, and we applied our interpolation method to a Gaussian line with the same sampling as in the SOLIS spectra. And based on that, we determined that our interpolation error is about 1 centimeter per second. So our numerical process here doesn't add significant noise to the spectrum. We can measure the real astrophysical changes in the line bisectors. Now, first I should say there's substantial previous work on solar line bisectors. High-resolution spectra have been taken on the disk of the sun in magnetic regions versus quiet regions, but not for integrated light over a full solar cycle, especially with multiple lines. So we've measured 19 lines over the full solar cycle in integrated light, and I've shown you some of the bisectors here. Now, these bisectors that I plotted here are not individual bisectors. SOLIS measures once a day. So for each SOLIS spectrum, we get one bisector of each absorption line each day. And what I plotted here are the average of many bisectors for a quiet sun period, meaning the average magnetic field is less than 6 Gauss, and an active sun period, the average magnetic field is greater than 6 Gauss. And that 6 Gauss is somewhat arbitrary. We have to make a judgment on what we call active and quiet, but we varied it. And we found that our results are not extraordinarily sensitive to where we do the cutoff between quiet and active. And you can see that in the case of this line on the top, this iron line at 539.318, it's my favorite line in the solar spectrum, but I guess I'm the only one that really likes it. But you can see its bisector has a C shape. And in the quiet sun, that C shape has a greater span. We measure the span of the bisector as the distance in wavelength from the core of the line, the lowest flux point in the line, to the inflection point where the curvature begins to turn around. So that span of the line is less when the sun is active. The bisector is C-shaped because of solar granulation and the velocities in solar granulation. When the sun is active, the magnetic field tends to suppress those granular velocities, and thus the line becomes less C-shaped and more symmetric. Not all lines are affected very much by solar magnetism. This ionized titanium line in the middle panel is essentially the same in active regions, in active phases of the sun, and in inactive phases. And there are some lines, the strong line, this calcium line at 854.2 nanometers, this is a very well-known line. It's formed in the solar chromosphere, and I'll talk a little bit about these. This is an inverse C-shaped bisector, and inverse C-shaped bisectors are not well understood. So the strongest lines tend to have these reverse C-shaped bisectors, and we don't really understand why. Nevertheless, we do find that solar magnetism tends to suppress the span of the bisector and drive the line towards greater symmetry. Here are some results where each point in this plot is a bisector measured on one day. So solar magnetism reduces the absolute magnitude of the bisector spans. Lines become more symmetric. The C-shaped bisector at the top, the red dots are the active sun phase. The blue dots are the quiet sun phase. The x-axis here is just the average magnetic field, and we just cut it off here at 6 Gauss. You can see when the sun is quiet, there's a locus of points that are well above the bisector span when the sun is active. The titanium line in the middle doesn't care about solar magnetism. The calcium line on the bottom cares very much, and the change in the span of the bisector is about 50 meters per second from quiet to active regions. It's somewhat puzzling that the reverse C bisector spans are also reduced by solar magnetism, and I'll explain why that's puzzling. But first, here's my favorite line. This is 539.318, and this is the span of the bisector plotted versus time. And then we took the average magnetic flux, and I just inverted it and scaled it to agree with the data. You can see very nicely the span of the bisector tracks the magnetic field strength on the disk. In the sense when the magnetic field is stronger, the blue curve is inverted, so the strongest magnetic field is downward here. In that case, the bisector span is reduced. And the effect is about 10 meters per second over from quiet to active regions on the sun. Now, I want to talk about reverse C bisectors a little bit. They're poorly understood. We still do not have an unequivocal explanation of why some lines have bisectors that are shaped like that. One possible explanation is that these are the effect of shock waves. Motions in the sun, if there are sound wave, well, we know there are sound waves. The solar P-mode oscillations are standing waves. If there are propagating sound waves, their amplitude will increase as they propagate upwards into the chromosphere that's sensed by this line. And it's been demonstrated that they could, in principle, cause a reverse C bisector. Another possible explanation, there's this paper in 2014 by a solar group, I believe they're in Denmark, in which case there is, if you combine isotopic splitting, Zeeman effects, and line saturation, you can get reverse C bisectors. And the way this works, so the black curve here is the measured spectrum of this line with an FTS. And then there are two modeled curves with and without splitting in blue and red. And these gray lines, the vertical gray lines, are the positions of the line in different isotopes. Different isotopes have different weights, and so the atom absorbs at a different frequency. So when you look at this line, the main isotope has one wavelength, the other minority isotopes have different wavelengths. And if you account now, if those lines were all symmetric, the net result would still be symmetric. But when you add Zeeman splitting and the fact that the line core tends to be saturated, then in the blue curve, when there's a Zeeman split effect, well, first of all, that isotope is not centered on the main isotope. So the Zeeman pattern is shifted, and one Zeeman component is centered on the main isotopic absorption that's saturated, so it doesn't produce any additional absorption. The other Zeeman component is in the wings of the main isotopic line, and that's unsaturated, so it produces an absorption. So that produces an asymmetry of the line, and if the magnetic field changes, that effect will change, and it will cause an asymmetry of the line and a net radial velocity shift. So this is an example of the kind of complex effects that can cause false radial velocities on the sun. Now, if this mechanism is really dominant, it has to occur to some extent, but if it's really dominant, then we would expect the line bisectors to have the opposite behavior of what we see. So this is probably not a dominant effect. This would cause the line bisector to be it would increase the span of the bisector in when the sun is active, whereas we see the opposite effect. So the big question, I wanted to say we don't care about the physics of the sun, but we do care about the physics of the sun. But what we really care about is, can we recover precise radial velocities in the presence of changes in line shape? So we inject a radial velocity synthetic signal into the data. The SOLIS data are all in the heliocentric frame. The spectra have all been shifted to be coincident. We inject the synthetic signal. We make that synthetic signal the Earth. Its amplitude is 9 centimeters per second. It has a 1-year period. We then decompose the bisector of each line. I am very fond of simple analyses, and a principal component analysis is a simple analysis. We decompose the bisector of each line with PCA, And then we take those components and we fit them to each individual bisector. We use the most significant components. We don't use all of the components. We only use the ones that are needed to fit the line to within the observed precision. If we used all of the components, we would be overfitting. Included in the principal component analysis is a 0 point in wavelength. And then after we do that PCA fit to each individual bisector, we save all those 0 points and we average them over lines and we average them over phase. And that 0 point contains the injected radial velocity signal. And can we recover it, or have these changes in line shape obscured it or contaminated it in some way? So we attempt to recover the Earth. One of the things we noticed when we did that, well, single lines are certainly not, even in the solar spectrum with lots of photons, a single line is not going to allow you to measure the radial velocity of the Earth. So it's not, you just don't have enough photons in a single line. So they're not sufficiently precise to recover the Earth. But here, as a function of the phase of our injected signal, is the radial velocity of my favorite line at 539.318 nanometers. And it is, alas, affected by telluric absorption, or what's called microtelluric absorption, because it's pretty weak. And a lot of stellar spectroscopists would ignore the weak telluric line. This solar line, there's a telluric line slightly redward of line center. And because our injected signal has a 1-year period, because we're trying to make it like the Earth, it's phased with the climate on Kitt Peak, actually seasonal variations in water vapor. Kitt Peak, in July and August, there's the summer monsoon, water vapor increases, and you can see that the radial velocity of this line tends to scatter upwards in those months. It's being pulled slightly to the red by that microtelluric absorption. We didn't make any corrections for telluric absorption. You could probably reduce this if you made telluric corrections, but what we do is if we have a line like this one that is affected by microtelluric absorption, then in our exercise of recovering the Earth-like velocity, we just omit that line. Nevertheless, we have 19 telluric-free lines, and even with the solar spectrum and the high signal noise of the solar spectrum, if you want to recover a 9 centimeter per second signal, you still have to do additional binning by averaging not only over lines, but also binning in phase. So this is binned in phase. So here is the recovered radial velocity signal as a function of phase. The solid line is the signal we injected. The dashed line is a least squares fit, allowing the amplitude and the phase and the period to vary. And to within the random errors, we can recover the Earth. So this analysis has some limitations. The good part of it is when we injected the synthetic signal prior to doing the PCA bisector, prior to analyzing the bisectors. The synthetic signal was in there at the beginning. But a limitation is that it was injected after some phases of the data analysis, in particular after the continuum was rectified and placed. Now, the reason for that is that we got the data that are released by the National Solar Observatory already have the continuum placed and rectified. And we didn't want to go through the very extensive exercise of going back to the raw data. So it's in principle, it could be that there is some aspect of placing that continuum that would contaminate our analysis. But at a very minimum, what we can demonstrate is that changes in the line shape by themselves, the line shape per se, do not prevent the extraction of a Earth-like radial velocity signal and will not prevent EPRV Earth detections. This is just a line bisector restatement of what Andrew Collier-Cameron and Eric Ford and their collaborators concluded based on the cross-correlation function in 2021. We've come to the same conclusion using line bisectors. So what do we want to do next? Well, there's a tremendous amount of solar sun as a star, radial velocity relevant spectra out there. Spectra are being obtained every clear day on the sun by NEID, by HARPS-North, by EXPRES, also KPF, and also Pepsi. And we want to measure those line bisectors also and try to repeat this analysis on individual lines. We will be able to do many more lines because we will not just have segments of the spectrum, we will have the entire spectrum from NEID. Now, a possible downside of using those spectrometers is their spectral resolving power. I know they're high spectral resolution, but SOLIS was a resolving power of 300,000, and it was a double pass spectrometer. So the spectral purity of SOLIS is very high. This figure shows this is a synthetic line. It's a Gaussian line, but it's a Gaussian line to which we have added another Gaussian line to make it asymmetric. And thus it has a bisector. And this black curve is the bisector. And of course, it's on an expanded scale. If you plotted it on the real scale, you'd be hard to see the curvature by eye. So this is on an expanded scale is the bisector at infinite resolving power. If we then observe this line at a lower resolving power with SOLIS, you get the orange bisector, which is close to the infinite resolving power bisector. And then with EXPRES and HARPS-North and NEID, you get some curvature, but not about half as much as in the original bisector. So those bisector spans that we will measure with NEID, HARPS-North, and EXPRES and KPF, those bisector spans will be lower due to the lower resolving power, but they'll still be useful. And we expect to be able to measure changes in the bisector as a function of solar activity, and to be able to demonstrate that we can recover center of mass radial velocities in the presence of changes in the bisector and in the presence of line blending, we hope. And maybe the most important statement in my talk is right down here. We want to find lines that are the least influenced by solar magnetism and the least affected by line blending, that is, an indirect effect of solar magnetism. But the data volume is very daunting. So I'm currently working with the NEID data, and I have tens of terabytes. And even with tens of terabytes, I was selective. And there's so much NEID data, I can afford to be selective. So NEID has a pure heliometer. And this is one segment. This is a 10-day interval, which is just an arbitrary interval that I picked. And this is the output of the pure heliometer, measures the total flux from the sun over all wavelengths. So it's not a spectrum, it's just photometry of the sun. And each curve here is the sun rising and setting during the day. And the noise are clouds that pass across it. Well, clouds are bad for the spectrum of the sun as a star because they're not spatially homogeneous. So they can block one limb of the sun more than another. And the radial velocity of the sun is, let's see if I remember the number, it's 1,800 meters per second, I believe. So I can be corrected on that if I've misremembered it. But it's large. And so if you block one limb of the sun more than another, you'll have a spurious radial velocity signal. So I'm very selective about the data I'm picking from NEID. I pick only the clearest days and not even if there's a little bit of cloud. But already I have tens of terabytes. And so what I'm going to be doing this summer is measuring the line bisectors and the radial velocities of individual lines in the NEID spectra, and also beginning to do that in HARPS and KPF and EXPRES. So to summarize, we analyzed tens of thousands of bisectors of 19 lines in the SOLIS ISS spectra. And those lines vary in response to solar magnetism. And both the C-shaped and the reverse C bisectors are reduced by solar activity. I didn't quote the statistical numbers, but about half of the bisectors that we measure 21 lines, about half of those lines have a statistically significant effect between active regions of the sun and inactive regions in terms of measurement of the bisector. And in all but one case, the bisector becomes more, the lines become more symmetric when there's magnetism on the sun. The one case is just a very weak line, which is probably not typical. And that increase in the symmetry applies both to the C-shaped bisectors and also to the reversed C-shaped bisectors. And we've done a test where we inject and recover an Earth-like radial velocity signal. We can recover that radial velocity signal in the presence of changes in the line shape. And our analysis has limitations because we're presented with data in which the continuum has already been rectified and some other data analysis steps have been applied. So it's conceivable that if we did the analysis beginning with the light as it came in the spectrometer, that is beginning with the spectrum as the sun produced it, then our results might be degraded by our data analysis steps. But at a minimum, we find that the changes in the line shapes per se do not in themselves prevent the EPRV detection of a planet like the Earth orbiting a star like the sun. And I will stop there.
Excellent. Thank you for a wonderful presentation, Drake. I invite folks to use the little clapping hands emojis to show that you are keen on the talk. Before we jump into questions, Doris Dow, who's one of our headquarters program officers, had asked if she could make a brief announcement. So I thought, Doris, if you're ready for that, we could do it while people formulate their questions for Drake, and then we'll come back to the science in a moment.
Sure. Thank you. First of all, thank you. Really wonderful questions. Just to let you know how I was anticipating is I canceled a doctor's appointment so I can listen to your talk because it's like one of my favorite subjects. Anyway, my announcement. This is where I am holding a pen and pedal. Please help. So as you may know, we are coming to the deadline for proposal submission for the second cycle of precursor science. Okay. This cycle, in my opinion, is even more important because this is where we really need to do some programmatic decisions at headquarters. As you know, we've already been funding 11 projects under the cycle one. So I want to make sure that if there are any gaps that are really urgent, we fill them. This said, guess what's coming? If you are not part of proposal, if you are not a paid a co-I or definitely a PI of a proposal for the second cycle of precursor, I am in dire need of reviewers because everybody and his cousin and her cousin are applying. So there's a lot of conflict of interest that I have to navigate. So I really, beg your indulgence and I'm normally very kind to my reviewers. I don't overwhelm them with email. I don't overwhelm them with responsibilities. So the more reviewers I get, the less you have to read. See, I'm sweetening the pot. So please send me an email. Volunteering if you are not a paid person from a proposal. That's all. And thank you for the presentation and for giving me the time to talk.
Yeah, of course. Doris, why don't, if you have a moment, pop your email in the chat so that people can grab it easily. And then, yeah, folks, if you are willing and able to help out, I'm sure the community would appreciate it.
Yeah.
Okay, with that, questions for Drake. Please feel free to use the raise hand feature or just unmute. Drake, can you say a little bit? Oh, no, there we go. Andrew, go right ahead.
Well, it was a wonderful talk, Drake, and really, a very different approach. And it's good to see these, well, essentially what you've found. One of the things that's worrying us most at the moment is not so much the magnetic effects as the granulation, and in particular the supergranulation effects. Because one of the things that worries me, particularly with supergranulation, is that you have extensive patterns of horizontal flow on the surface, which essentially move the fluid in bulk and may well introduce Doppler shifts without affecting the bisectors. Is there anything that SOLIS ISS can do in order to quantify that effect? I know you mentioned that there was a bit of difficulty establishing the 0 point, but is that something that you think might be doable?
So although I said there's not a wavelength calibration, the one segment, the segment that contains that high excitation carbon line, was they did obtain exposures with an iodine cell. So if the iodine cell is stable, iodine cells have complex spectra, but if you deal with that, you in principle could get velocities, and you could get velocities of that carbon line that is formed deep and maybe more sensitive, maybe sensitive to supergranulation in that respect. So that's worth looking into.
Yeah, no, I think that would be very valuable. Thanks.
Yep.
Okay, and Lily, go right ahead.
Hey, Jake, thanks for the talk. I really love that simulation you did where you showed how the bisector measurement changed with resolution. I'm wondering if you've tried injecting like different bisectors and seeing how it scales with resolution. Like, is it a linear offset? Is it just an offset? Is there like a linear relationship between what the bisector should be and what you get from the degradation in resolution? I feel like this matters if we want to combine data from different instruments with different resolutions.
So we made one bisector, and we made it by using, it's a combination of Gaussian lines that have different strengths and wavelengths. I think you could do something more systematic. You could do an array of bisectors and study them. That would be a good project, but we haven't done it that extensively.
Okay, that's a figure I'd really love to see.
Yep.
Thanks.
But that would be well worth doing. That would be a great thing to do.
Thanks.
Yeah, Andre Silva mentions in the chat that POET, which is the solar telescope that's being commissioned at this point, I believe, for Espresso, will also allow the probing of impacts of granulation and supergranulation on the sun. So keep an eye out for that. Excellent.
Good.
Okay, any other questions for Drake? Oh, Andre, I see your hand. Go right ahead.
Yeah, sorry, just a small correction. The commissioning is going to be in early 2025. We're currently building the telescope.
Ah, okay, thank you.
Okay.
So eye out for that.
The sun will still be there in 20. I hope it will be there in 2025, and it'll still be active.
Yeah. Andrew.
Yeah, just harking back to what Lily was saying about the degradation of the curvature of the bisector as you degrade the resolving power of the spectrograph. Do you have a feel for let me see. You've got 19 lines. Over the HARPS North or NEID wavelength range, of course, we've got thousands. For each of these instruments, do you have a feel for how the wavelength range and hence the number of lines that you can address compensates for the degradation of the measurement in the curvature?
So I don't have a feel by actually calculating bisectors for NEID yet. I'm in the process of working out how to do that, and dealing with the shell shapes and all that. But just look at the numbers. You have thousands of lines. The bisector amplitude is reduced by a factor of 2, but just you have thousands of lines. Square root of thousands is bigger than a factor of 2. You should be able to do really well with NEID and HARPS North and EXPRES.
Yeah. So we shouldn't be too depressed about it.
No, I'm not depressed about it at all.
Good.
I cannot believe we're saying an R of 175,000 is degraded. This is ridiculous.
Yeah, to me, it's all, I used to work with a laser heterodyne group. It used to work with spectra resolving power of 10 to the 6th. So it's all low resolution to me.
Okay, on that note, let's call that for this month's colloquium. Thank you again, Drake, for an excellent presentation. Thank you, folks, for wonderful questions following up. We will reconvene next month on May 23rd with Jean-Baptiste Delezay, and I hope everyone has a great month between now and then. I will see you guys soon.
Goodbye.
Right. Bye-bye. Thanks, Drake. Thanks, everyone.
Thank you.